Hello, how are you doing? Okay. So we have about a minute. I am going to touch back on the lab before we start because I started grading the lab and I think some of you did not include the answers, possibly because you didn't know how to address the questions. And then, we'll talk a little bit about it. Okay. And then we will continue with chapter 4 notes and assignments or unit 3 assignment. Okay, so it's 6 o'clock. I'm gonna go ahead and get started. Oops, sorry. Let me get back to here. Okay, so we are gonna cover chapter 4 today. If I have time, I'll touch back on some of the GATES tool and give you some resources because I think a couple people were having questions about whether this class is going to address some additional knowledge in digital logic. It was not written with digital logic in mind. It was written as assembly programming as a curriculum. So that's my major emphasis, but I think some of you are interested in going for engineering, either electronics engineering or going into computer engineering where you want to maybe work with building processor and so on. So I'll share with you some tutorial resources. If I'm not able to do that, I will be able to either put it in an announcement. I did add an announcement recently. I haven't had time to add it for all my classes. I'm planning to put it on my CIS7 course room announcement. I didn't put this as a scheduled announcement, so it probably didn't send it via email. But if you do get a chance, please check out the opportunity. We had quite a few students actually 4 students that had gone through the fellowship program. It pays $5,000 for 10 weeks, and you will be required to participate at UCR. I am the leading faculty for RCCD, but mostly for MVC. MVC has a data science degree and also certificate. We want to launch the classes possibly in the fall. So if you're interested in that, you can start taking. I think we already have Python programming, but for the data science classes, we are gonna roll it starting the fall. But for this opportunity, it is a fellowship called DS Path Fellowship. It is part of the National Science Foundation grant. If you have taken my classes, you know that I participate in grants to be able to build out, work experience like apprenticeship, and also scholarship for students. I really believe in that if students have the resources, they will be successful. So this opportunity, you can apply for it and you will work with UCR students, grad and undergrad students through the training. At the beginning, they will go over the basics, and then eventually throughout the program, you learn how to work on a data science project. You will be given a real case project, and you will have a mentor. So, for example, a project could consist of looking at how we can have water systems based on the data that we have for some of the lower basin or some of the inner city area. or it could be on traffic with Riverside County, looking at transportation and highway pathways and so on. So they have the data to do that, and they actually have analysts and scientists that will work with you. It's first come, first serve. We will have an info session, I want to say in a few weeks from now, for RCCD students. So what will happen is the faculty from RCCD, there are 4 faculty, I and 3 other faculty will vote on the qualified applicants. And it's based on, how you have proceeded through your programs, looking at your transcript and your information and all of that. So all the qualification information on the application, make sure that you've put that in, and it needs to be completed by March 31st. The selection process will take place in April, and then you will be notified in May. The program will start in the summer. Last time we rolled it in July all the way till August. And so what you will do is you will be able to, go through the training and participate, and you will receive a stipend check via RCCD for $5,000. Okay, yeah, Lily had put that in, and if you have questions, you can ask Lily. She did really good in the fellowship program, and she'll be happy to talk to you more if you have questions as well. But you can also ask me if you have questions. So we'll have info session. I will let you know when the info session will be. It will likely be on a Friday, where you will meet all the faculty that is leading the program, and then you can ask questions then as well. Okay. So June 23rd to August 18th is the projected timeline. And if you are in this fellowship program, you will be committed to this timeline. So, if you're leaving the country for vacation or anything like that, that will omit you from the program. So make sure that if you want to do this, you will be required to attend sessions during that timeline. Okay, all right. So what we will do is I want to touch back on Lab 2 real quick. The reason why is I think I did receive some questions regarding Lab 2, and as it is our first assembly program, I know that some of you did really great and you already submitted your work. Also, when you turn in your lab to me, please make sure that is PDF or .doc, because I cannot view other type of files like .pages from Mac OS. I use a Windows PC, so I won't be able to have the application to be able to view that, and I think I put that in the submission information. And when you do the lab, the point in the lab is to allow you to build the program, but also understand. So take the time to go through and answer the questions, because those questions is gonna let you go back and look at the code and evaluate the code and be able to understand a little bit further. I know that we're very new to assembly for most of us. So as you go through it, if you are stuck on something, you can ask me. And also just to dissect through your code and understand it, it's gonna be really important, okay? So I'm gonna address 2 of the questions, and then we'll move on to chapter 4. So from the last lab, what we did was we did a program where we used a simulator after we wrote the program to assemble and then run the program. So this is the code for the program, and it's taking the value that was set, which is it loads. So you clear out the register, you load to symbol. So that's equivalent to what you would see as your variable initialization and your data you filled here. So you initialize the value hex 2 and 30 hex here. And so when you add that, you're going to have 32 hex, which is equivalent to the character 2 when you look at the ASCII table. And so when you go through and you just explain, why did you get the output, right? What is your output? You got the 2. And why did you get the output? Because what we did was we manually convert your hexadecimal value, which we fill, after we add to be able to receive the hexadecimal too. Okay. Yeah, that will be fine. So if we do submit, right, if you work on the dot pages, you just use the program to save it as a dot PDF, and then to be able to upload it. So you can upload the screenshot separately if you like, and then type up, use Google Doc and type up your answer and questions, or download the Word document and then type in the answer underneath right here, which most of you did, and then add the screenshot and then submit it. So you can put it all in one document. That will be great. Yep, no problem. Okay, so as we were saying that we got the character 2 because of the ASCII conversion that we manually did that, right? And so in order to change the program to make it another number, we have to change the initialized value here, okay? So if we change the value that we initialize here, or what we can also do, you're going to learn this week, that we can add it to a register. We add one more line and add the differences between the 32 to an equivalent ASCII value of the hex 9, then we would be able to have the hex 9 as the output. So you simply look at the ASCII table and you would see what is the hexadecimal equivalent for 9, okay, or the character equivalent for the hex 9. And that's what you're going to incorporate in your code. You can either fill or you can add to the existing register, which is register 2. So if I add another line here, let's say I want to say that I can add R0, because R0 has our sum output, and at this point it should be 32. So I just need to find the difference from hex 32, right, to be able to output 9, right? So give me a second. Let me go to ASCII table. And so I can show you. So if I have a 2 right now, and it's hex 32 for that program, and I want to output 9, so it's going to be 39. So what I can do is in the program itself, I can add another line. If I don't want to change my fill, I can simply add another line. So we want to be the sum here to be 39, right? And in the previous line, we know that it's already here. So we're going to take R0, and we're going to add a hex 9. I'm sorry, a hex 7. So a 7 plus a 32 is going to give you a 39, which is going to be equivalent to a 9 output. So that's one way. Another way is I can change my fill value for num, and you can use lowercase too, to hex 09. And that can change the program itself between, a 32 hexadecimal value to a hex 39, okay? So if I add the difference, which is a 7, to the existing sum, I would, because this is 32, right? Add it with the 7, that's going to give me 39, and it's going to store the 39 here. And that's where it's going to output is the register 0. Or I can modify the program by just changing the fill value, which is for the num line right here, for my data initialization to a 9, and it should be outputting 39. Yeah, so ideally, you should be able to use upper or lowercase, but in the editor itself, it wants you to have uppercase. So my practice, that most of the emulator, the simulator, or a lot of the editor for assembly, we type in caps, okay? And you can comment in lowercase so that way it's easier to read, but in your program, you should have it all caps. So yeah, Sierra, that's right. Okay, but there are some editor that allows you to use lowercase, but just good practice. We're gonna use all uppercase or all caps to type our code. Okay, any question? So that's for 17, right? And then I want to come down to these two questions. And there was some confusion about input. So the program, if you look at it, and I said this last time, there's a limitation in this program. You're going to see in the future week that the scale for the ASCII conversion is off on this. Yes, it did output the sum of the two inputs. So if I put in a 1 and a 2, it's going to give me a 3 as a sum, as the output. But what happens is when you use any values that's higher than 5, and you can only input one single character at each of the input. So let's say that I put in a 6, right? And I'm going to pull up my calculator, and so just to avoid reassemble and simulate for you. So if I input my character 6 and another 6, in human context, that will be a 12, right? And so in the hex, that should give me a C. But when you input those, you will not get the exact value as what it should be, okay? Or if I have an 8 plus an 8. So you do see that the scale, right, for your offset for the hex, when we subtract 30 and add 30, it would only work for the values from 1 to 5. So this program is not fully correct in that it's only able to convert a range of characters, right, from 1 to or 0 to 5. But then when you use symbols, you might not even be able to get anything, because what happens is when you look at the ASCII table, so if I input in a plus sign, right, that will be 2B, okay? And when you look at this, each of the hex character is 4 bits. 4 bits. So in a word size, based on our instructions, when we add things in the opcode itself, when you have the opcode, it's already 4 bits. 2 bits is going to reserve for other things. We're going to talk about that. And then your value is only going to be the 5 bits. So what happens is it's not able to output anything, or it's able to output the wrong symbol based on the calculation. It's either overflowing or the scale for the ASCII table, that with the ASCII in the program is wrong. Okay, it's not fully correct. Okay, because when we're using offset 30 for hexadecimal, that will not fit in other areas, especially when we're looking at other characters and other values, okay, higher than 5. So you're going to see a little bit clearer on how to properly set up an ASCII conversion when we will approach it several ways. So the reason why I want to include that program, so that way you can look back and see that even if it outputs somewhat correct in a certain range, outside of that scope, it's wrong. And you do see that a lot in software engineering, that sometimes you're going to get a working program and it works and it shows values, right? But you got to test it to its maximum capacity. And sometimes when you see that, you're going to have to see how you can overcome the limitations, because sometimes users would input other values outside of the range that you intend for them to input. So on this program, definitely there is a limitation. And so when you answer these questions, right, you look at your output and you can look back into the ASCII table and ask yourself, is the offset, is the hexadecimal value that I initialize or I fill here, is that going to work for all of the other characters? All right. And then will that work for the symbols or anything in the higher range or even the lower range? All right. So I just want to touch back and clarify that so that way in the future, right, when you look back at your assignment, you can fully understand how to do that. Any question regarding lab 2 for now? Okay, so let's close that. And I'll go ahead and save that. Okay, so now let's talk about Unit 3. And you can find the notes in Canvas. So this is going to bring you back to the very basic. Because in order to really understand at the low level, we really have to understand the very basic functionality and how the system is built, right? Throughout the classes in programming, you probably heard of computer models and you understand how to use your keyboard and mouse as input devices and so on. So we will clarify all of that because you're going to see the mechanical side of things on how we operate at the low level to really tie that into the coding piece. Okay, so for the basic definition, a computer program simply is going to be a set of instructions that's going to be defining some form of work for the computer to be carried out. And ultimately, everything breaks down to binary and everything adds. Okay. So for your instructions, we would want to make sure that we intend for it to execute some form of work. For example, if you open an application like Microsoft Word or Adobe or even a game app, right? There is some form of execution that's happening in that particular program. So we should ask ourselves, what is instruction then? And ultimately, it is a piece of work that's specified in the computer program and coming back to here, right? So going back to lab 2, our instruction could simply be adding values together, right? But at the register level. So, or load some kind of label to a register, or add a numerical value like a decimal to a register. So with that, it is specified in your code. So since the 40s, John von Neumann proposed the fundamental model that continues to be applied today. And it's very basic. There are 5 major parts in your system. Okay. In a computer, we need to have a storage component, which is going to mostly, when it was originally built, it was memory. Hard drive actually came later, and then solid state drive is more recent. But back then, primary storage was just memory. And memory is continued to be used today in many different forms. That could be internal to your processor, or it could be external outside of the housing of your processor, or it could be RAM, on random access memory. An application requires memory in order to run, right? Because it needs to load all of the instructions and the data into a location of memory to really be able to fetch it in for execution. And our system, our computer system, consists of a processing unit, hence the processor. And we focus more in this class on the microprocessor, but we have to see how it plays in the major overall system architecture. Then we have to have a way of input, how we bring data into a system and how we can extract data out from the system. And we need to have some form of coordination to control, right? Could be processes. And so that would be control unit. later on that we would see that the processing unit and the control unit combine, okay? And so this is how you would look in a diagram format. And the MAR here it stands for Memory Address Register, okay? Memory Data Register. And so the address register really handles just the actual location where the data is stored. And so remember that register files are just temporary. And so when we work directly with the registers, what's going to happen is it's either going to point to the location or it's going to store at that location. And so with that, it needs to be able to communicate with the processing unit, hence your processor. And inside the processing unit, you would see, and we're going to see a lot of this starting from this week, is going to be arithmetic logic unit, which is your ALU. And there's a temp location. And in order for the ALU to really see what's required, right, we would refer to this. And a lot of this come into play with cache and things like that, what's in the processor. So when you purchase your processor, you see certain processor would have a certain storage size internally. And some cache is inside the housing of the processing unit and or outside. Even though it comes on one processor, as you see, oh, when you open the package, right? But inside the housing component underneath, you see that some's built within and some's out. And also, you would see that your input and your output, right? This is how we bring data in. This is how we bring data out. And this could be printer. Now, sometimes you would have I/O device combined, right? So for example, if I'm using a laptop that has touchscreen monitor, I'm able to input, which is I can touch it and select something, right? Or I can draw on it. And I can also output to display text from it, right? So sometimes you would have a device that would work with both areas. And then down here, you are going to have the control unit. And remember, I said that this is really for coordination. It's for coordinating the activities that's happening or the work that needs to be done, especially when you're thinking about your current processor, where it really has, right, multi-core and how we're able to execute things simultaneously, right? So in my advanced Python class, I talk about like when you're looking at a sequential program compared to a parallel program, how is it really pooling the task or the processes to be able to execute things simultaneously? And that's really coming down to the developer and the designer, the engineer that really built the system. So the engineer already built the processor to be able to execute things simultaneously. We just need to code it and making sure that it's coordinating the activities and to make sure that it's parallel, meaning that the cores are at work at the same time. Okay. So we are going to touch on the control unit, how it's going to be able to look at the queue. And then when we're going to come back to a lot of this, and you're going to see later on as you proceed when we're working with stacks, right? How things are pulled from certain location and be able to put that onto the stack so that way your programs ultimately is compiled at a higher level. So here I give you some of your basic definition or functionality. Your memory contains instruction and data. That's its job. The processing unit perform calculation, arithmetic, and logical instructions. Control unit interprets the instructions. And your input is to transfer data into, and output is to transfer data from memory to a device. Okay, so let's answer some questions. So For number one, we need to define, and you can grab it directly from the notes, or you can type it to summarize it so you remember the components and function of the von Neumann model. Remember, we have 5, and make sure that you know these 5 for our quiz and exam. We have memory, as I said earlier, contain instructions and data, processing unit, control unit, input, and output. And don't answer 2 yet. We're gonna look at 2 shortly. Okay. And you can find the answer coming back to your notes, right? That's from page 1 to page 2. So let's go into each of the section now. Let's look at the array of memory. So in this example, it tells you that you have 256 megabytes, which has 2 to the 28th power of address space. And that means that we have specific value or identifier for each of the space using k-bits. And the m bits is going to represent the value stored in that location. Okay, so when you look at this picture, right, we would have a group of memory addresses, and we would use the identifier to really identify the location on the memory itself, and then the m bits are the values stored in that location. Now, at the higher level, when you're looking at operating system, the way that it pulls file is really depending on the file system that's used for that particular software. Okay, but ultimately, when we're looking at the low level, right, everything needs to have an address space. Everything from the software view, everything that you write in your code, it will put to a memory location, and it would assign an address. Okay. So what is it really doing inside? The things that happens in memory is that we can load to memory. So this allows us to read a value from a specific address. And when you do a load in this class, what happens is it's going to place the address at that location into the MIR. So think of the MIR, the memory address register. What that is it is a list of addresses. Okay. It would store the address information or the location. Okay. So it needs to keep track of the address. So the MIR's job is to keep track of the address. And then it interrogates the computer's memory. Now, the data that you actually put at that location, it's gonna place in the MDR, hence data. Okay. So when you place data at that location, the MDR is gonna track that. So these two are the major components that is used for load. So in this example, if I load, right, the address A into the MAR. So if I do a load, a location, the address, let's say A, is going to go into MAR. When we read the information, it's going to send a read signal to the memory, but it's going to read from the other register, from the MDR, because MDR actually has data information. Okay, so these two registers work together so that way we can load. We can read a value in the memory from the location in the memory. So when you're running your application, this happens instantly all the time. Okay, when you play your game or any application that you run, there at the low level you have loads. Any question? So that's different than store. So when we store, we really write the value, right? When we load, we read the value. So when we write the value to the memory location, these are the steps. It's gonna write the address, which is the location, to the MAR, which tracks the address. And the value, again, is stored to the MDR, very similar to load. But for the write, when we store, it's going to interrogate the memories and it's going to write enable signals. So it's a different signal that is going to be set or sent, asserted. And so the information, your data, is going to be in the MDR, which is then right to the actual location that's identified in the MAR. Okay, so think of MAR referencing the address or the location where the data is actually stored. And so when it writes, it needs to use both of these register because the MAR is where it's going to place it, and the MDR is what is being placed there. And here's the example for that. We write the data X to the MDR because that's the actual data, and we would write the address to the MAR. So when you need that, what's going to happen is it's going to go to the MAR to find the address A to be able to access data X. Okay? Any question? Okay. So now let's come back to our assignment. And I'm sorry I wrote it in red. I can change this because sometimes that's hard to read for. Okay. So if a system has 512 megabyte of memory, what is the maximum address space? And if you do look at their PowerPoint presentation, they do give you a brief little information, but here I type it out for you so you can understand. We understand that the address earlier we saw 256. So let's come back here real quick. I'm going to come back to the top right here. So it tells you that this is 2 to the power of 28 is 256, right? The simple calculation for this is you have log 2 of n bits to the address n bytes. So in the example, you can store 256 different values in the 8-bit number. Okay, so that means that 8 bits can address 256 bytes. So 2 to the 8th power, or 2 to the 28th, is going to give you 256 megabytes. Now, if you convert 2 to the 8th, that's going to be 256 bytes. So that's simply log 2 of n bits to the address of n bytes. If you have 2 to the 10th, then we would have 1024. So you need 10 bits to address every byte in a kilobyte. That means that you need 20 bits of address for every byte in a megabyte. Remember that we're working with megabyte here, right? And 30 bits address to address every byte in a gigabyte. So what will happen is you would see the increments of this when we go from bytes to kilobytes, right, to megabytes. And so if I take 2 and I raise it to the 32 power, this is my actual calculation for this value. Okay. So for 512 byte, we would use log 2 of, we would take 512, which is the given value here. We would multiply it by the conversion for the kilobyte, which is 1024. And then we multiply it again for the another 1,000, right, or 1024 for the megabyte. And so when we do this, and if you took discrete, you remember, right? So this is a distribution calculation. So you would take log 2 of 512 plus log 2 of 1024 plus log 2 of 1024, which gives you 9 plus 10 plus 10 equal to 29 bits. Because it's log 2, right? Another way that we can do this, it's also equal to natural log of 512 times 1024 times 24 divided by natural log of 2, which gives you 29 bits also. So there are 2 ways to do this. You can use log 2 of n or natural log of 2. Okay, and to do that, we would then simply take natural log with the conversion of 512 bytes to make it kilobytes, to make it megabyte, divided by natural log of 2, which gives us 29 or 29 bits. And so therefore we can conclude that 512 megabytes is going to be 2 to the power of 29 for the maximum address space. So you have to bring it from the bytes to the kilobytes, which is here, to the megabytes. And because the address, right, it's base 2, and we would raise it to the power of n, so that means it's log 2 of n, and this is how we would calculate it. Any question? Okay, no questions. And so for number 3, I touched on this prior to the address space. We talked about load and store, right? Read and write to memory. And the major difference is for the read, it used the read signal write enable for the store, and it uses the MAR for address, and it uses that address to find the actual data, and it uses the MDR to get the data. Okay. So make sure we know the basic functionality of memory operation. Make sure we know how to calculate address space. All right, so now let's move forward. So now let's talk about the processing unit or your processor. And so we would have the ALU, which is arithmetic logic unit in your modern processor. And So the basic unit or the basic quantity that it works with is a word or a word length. So your instructions are gonna be in a word. And so everything that we do in assembly in this class is gonna be 16-bit for the word length. Like I mentioned before, other processor or other architecture uses longer word length, like 32-bit or 64-bit. So when you work with ARM 64-bit, right, the word length is larger. That means that it's able to have other things, and it could vary also depending on the language that's used. So most of the architecture that you see word length is 16-bit, right? Like for Microsoft ASM, for x86, things like that is 16-bit. So in LC3, your ALU process 16-bit quantities, and a word is going to be 16-bit. Your word length is 16-bit. Make sure we remember that for exam and quiz. So each of your ISA has a word length. And I mentioned that it could also be 32 bits or 64-bit, depending on the architecture. So it's best when if you become an assembly developer, right, you would need to reference the architecture for your processor, how it's built, what is the word length that's able to work with. Okay. Like, for example, Snapdragon that's used in Android, right, smartphones, you would see that some of them use ARM64. Sometimes they would use like other ARM. And so you would need to identify the architecture and its word length and the type of assembly language that you use. And so in the lab, we already started talking about registers. And in LC3, there are 8 general registers. Some other languages, it might have more, like 12 or 14. But registers are simply just temporary storage. Think of it like a file or a temporary location where it would store. Nothing stays permanently. We can reuse it. We can load into it. We can add value to it. And its job is to be able to handle operands and store results. And so we would use these as location inside your 16-bit wide in our word. So we answered 4. What's your word length in LC3? That's 16 bits. And the function of your registers in the processing unit is it's in charge of operands and result of the functional units. Number 6 is very easy. That's the next section. So you can find all of this coming back to your notes. That's on page 2 and 3. Any question?
Yeah, I had a question.
Sure, Matt.
For number 5, it says results of functional units. What does that part mean right there?
Yeah, so you know how when we add the values in the lab, it has to store it to a register. Like for example, I'm adding add R0, R0, R1, right? R0 originally, let's say I have 2, R1, I have a 1, so it's supposed to be a 3. It writes that 3 back to the register 0. So that register 0 can be used for output or for other things.
So it's rewriting that register.
Right.
Okay.
So you have to have your result in the register to do other things. That's what it's saying. Is that you know, if your data has to go into your register, whether you sum it, whether you want to be able to access your data later, you have to put it into your register for other functionality. And when we write a function, we simply add the value to the register and then use it, or it could be a label, right? You have to load your label, like we load an address to a register, we load a label to a register. So the register is your middleman for all the functions, all the functionality in the processor, especially for this architecture. Now, if you're looking at like a complex, or instead of reduced instruction set, if you're looking at CIS, yeah, you do direct memory. So it doesn't go through register, you just write to memory itself. And it's more expensive to produce because direct memory is a different type of memory. And so therefore, you would see more mass production in this type of architecture. Okay. So we use register for everything. All right, 6 is really easy. I touched on input and output at the beginning when we talk about von Neumann, but we would see the information here. Okay, so peripherals are also encompasses devices, electronic components that would be referred as input and output categories, right? The most things that we use could be keyboard, mouse. Your output would be monitor and speaker. But you can also see scanner as input. And if you have a multifunctional device like, your all-in-one printer, that means scanner, copier, and printer all in one, like most of you would have at home or in your office. That is an I/O device. It's input and output. You can scan into it, you can print from it. Like we said about touchscreen monitor, that's more popular these days because consumers just tend to buy multifunctional device instead of buying multiple devices, right? It makes more sense for me to spend the money to buy one device versus many devices. And so you see that incorporated in our computing system, and it goes back to the 40s on how the concept of the computer actually expanded. And so with that, okay, I'm going to give you the breakdown. We're going to come back. We're going to spend one chapter on KDR and the other area. So when you look at your I/O, your input device has its own interface. That means that it is a way for it to have its own register, like MAR and MDR. So, for example, when we're looking at your keyboard, okay, your keyboard would have a register of its own, and the KBDR is for data. So this is how it's going to bring data into the system. And so when you do the in your program, right, it waits for the signal for the user to type. And when I strike a key, that value from that key is going to be put into the KBDR. And what happens is then it doesn't wait anymore because the KBSR is at work. It turns on 1. It sends a signal saying that, oh, the user already entered the key. There was already an input. If there's no input, the status is none. It's 0. It's going to keep waiting. And the programs just keep on running, or it won't proceed. It's just there at that line of code. Now on the console side, when you see display on screen, and you see this at higher level too, not just in assembly, right? C in, C out, print, and Python. For your monitor, on the data register, it uses the DDR. Okay, that's how it's going to be able to display the data. That's where it's going to save it temporary. And does it know when? Sure, it uses the status register, the DSR, to be able to check the status on when it needs to be displayed. So when I do an out on my LC-3 code, and it's going to go to the register 0 to transfer, right, the text or whatever value that you have there to the DDR. Update the status register saying that it's ready to output, then it's going to output whatever that's in the DDR. Okay. I love assembly. So like I really, it actually, you know, this course, right, it's intended to teach you assembly, but it really brings back everything that you learn, whether you learn about computer components, whether you learn about programming. It really ties back into the basic functionality, and you can understand the overall. And you can see it from the view of the compiler, and you can see it from the view of the system, and then the processor. So it makes sense in how we write our program and what is at work when our program is running. Okay. So as you're familiar with some of this, if you ever work with hardware components, right? Some of you have, some of you probably new to it. But in some devices, we talked about I/O. That could be your hard disk drive or solid state drive, external flash drive, etc. It could also be network devices like network attached storage, you know, for like servers. And so the program that control your devices is the driver. Many of you have Windows PC, you're familiar with this. So I was telling a student earlier today that came in for some help with my CIS11 class that when I updated my Windows 11, my touchpad driver failed, right? And I contacted the company that sell my laptop. They refer to their website for driver download. I updated, but OS always try to take over. So the driver ultimately is a software that control your device. Now, I explained this to my class last night when I was teaching cybersecurity, because driver is really important in that area too. Think of it like your device is like a car, right? You can have a truck, you can have a, you know, like any device could be a vehicle. Now, let's say that I have a device that's like a sport car. So for example, I went and I bought a $2,000 video adapter for my gaming system that I built. That's like the Porsche 911 or Corvette, or I don't know, something fancy. And then if I place a generic driver on it, a program that simply have the very basic functionality, that driver is only going to drive the car from point A to point B, but not to its maximum capacity, right? If I have a sport car, I want the driver to be able to drive it like a sport car. Okay. So what happens is in your OS, sometimes it places a generic driver. They design the operating system, which is a software that has programs to be able to control your devices for the basic functionality. Like if my mouse is to use to click, that's it, right? So for the video adapter, it will work, it will display, but not to its maximum capacity or its best. So let's say that if you bought EVGA, then you would go and download the driver, and to be able to have 3D simulations for your game better, the graphics is going to be better, you're able to control the GPU more. And so the driver is essential in that sense that it is also a piece of software that control access or how that device is being accessed by the processor. Okay, any question?
So the OS usually just does like a general driver, like just a
Yeah.
basic version of it.
Yes. And sometimes operating system driver is enough. For example, like USB. Okay. But let's say that if I buy a biometric reader USB and I plug it in and it's only seeing as a USB device, it's not functioning as a biometric reader. So what happens is I have to download the software to let the OS, the operating system, know that it is a biometric reader, right? So sometimes driver is generic. We call it generic driver. Sometimes it's very basic. It's just to operate. So the vendor driver is really intended for how that device is being accessed, okay, by another application or another software like operating system. Other questions? All right, so for 7, we can simply add that. You can add more to it so you can understand. So it's really a program that controls access to your I/O, your device. And in your, just this is side notes, right? So for your peripheral device, you can always update your drivers, right? So Microsoft does a few things. They use settings to be able to allow you to change that. That's just a way that operating system is managing your devices. But that's a new way for Windows. But you can also use other console, right? They have management console to be able to manage. So for example, like I can go to control panel to access all my tools and administration resources, but I can also have separate console, and everything is searchable on here, right? Like if you use Microsoft Windows PC, you can go to control panel and I can go to hardware and sound, or I can simply do settings. It's just, this is like sub applets to be able to allow you to go in and change, right? Your devices is also here, but you can also use control panel, which is the old way for the Windows. So they have to incorporate way to transition from the old OS to the new OS. Now, if you're looking at Mac OS or Linux, you also have ways to manage your devices as well. Every operating system, an operating system is simply just a software that interface with the user, allowing the user to be able to access the actual hardware, which is your computing system, right? But within that, it has to have the management capability to manage objects, which are your files and storage, and to be able to control resources within the system as well. So, all right. So let's talk about the control unit. Before I answer this, let's come here so you can see that's on the bottom of page 3 to page 4. So here is your control unit, okay? So the control unit really orchestrates the execution of the program, right? It coordinates everything in the program. So it has 2 components that's working within the control unit. Your program counter, which is your PC, and your IR, which is instruction register. So its main job are these 3 bullets. Number 1, it keeps track of which instruction is to be executed. So in a sequential program, like your code from lab 2, right? Top down, and in almost all program, like when you're looking at like a C++ program or a Python program, Python is very clear in that sense. It's going to go line by line with the interpreter. There's no, it's not using a compiler, but it's going to go line by line, and when it gets stuck at a certain line, it's going to halt there. Okay. So in that sense, the IR, the instruction register, it's going to go from one instruction to the next. But what if I jump, right? Like in your C++ program, what if I do a recursive function? In the main, I call a function that calls a function. So what happens is it's going to go to, at the end of that function, it returns, and then it's going to come back because the function calls itself, right? So it's going to come back to that block that you define as a function. So what happens is in the instruction register, it's going to track, right, which instructions at the low level to be executed within that block. So when it gets to the end of that block, because the function is being called again, the output, the return value from that function is then being stored and then pulled back into the function call again. So the IR tracks that. Then the second bullet says to keep track of which instructions to be processed next. So it's looking at the queue of the in queue instruction that's on the list for next. So it's looking at what's current and what's next. And how does it know that? So the control unit has a register for what is next. And we are going to use, when you look at stacks, it's going to be very clear. So what's going to happen is that register stores the address of the next instruction, and it's going to use that address for the next instruction. So that's how your program is going to go from one to the next when you look at your code. So they use the PC, and this is the program counter. And a better way to really refer to this is called the instruction pointer. It's pointing to the next instructions based on the address. Okay. So simply, this is your control unit. And so you can pull this section, or you can summarize it and you can put it onto your answer for number 8. Any question? So in the future lecture, we're going to refer to IR and PC. So make sure that we know what those are. And that's being discussed in this unit. Program counter and instruction register. We're also going to talk about MAR and MDR, because when we talk about load, right, and LEA and LDR and all of that, it's going to refer to these acronyms. So make sure that you know what they are and what they do. So now we define those. So in the future, it will be easier for you to understand like the functionality, the mechanical process that happens when we actually have a specific instruction like load or LEA. Okay. So again, question 8, go to your notes, page 4. And so for the control unit, it simply is to read an instruction from memory Yeah, and for this one, we're gonna talk about Q and NQ, but when mostly with stacks. This one you don't have to. For LC3, you don't have to do that. It simply is gonna go from one instruction to the next, unless we do a jump. We'll talk about jump later. So yeah, when we touch on jump, we're gonna bring that back a little bit. But you don't have to. So you can send, you can send it to a different area of your code by doing a jump, but simply it's gonna go from one instruction to the next for the line. So no, yeah, we don't have to worry too much about Q and NQ. So for the CU, for the control unit, it basically read the instruction from memory. That's where all the instructions are stored. Yeah. And that simply is, it's going to go to the address that's in the program counter, the PC. So the program counter have the address of the instruction of what's next, right? And after it read the instruction, it's going to interpret the instructions. And in the case where if we have a pseudo instruction like in or out or get C, right? We saw that in the last lab. It's going to generate signal for your IO, okay? Or sometime we would have halt, right? Stop. So that way it would then be able to go to the next work type of unit, right? So it's going to say, oh, in, I'm going to wait for the keyboard signal and the data. Out, right? I will have the data for the output and send the signal. So that's the only two areas that's really handled by the CU. Read instruction and interpret instructions. But with that, we have to see what's the current instruction and what's next instruction. So when it interprets the instruction, it could be from the machine cycle is complete, but it could be in one or many.
So it says interpret, but not execute, right?
No, yeah, not execute. Remember that all of these are small units of work. Instructions are small unit of work. So when you write a function, it's a group of small units of work. So when I define a function, for example, function get value, right? Like int get value. And then sometime in that I would say something like, oh, I want the user to input and store it into, this variable or this array or whatever. And so with that, right, when you do that, you're going to have like register and then be able to clear register. So in clear register and then add the value from the input, which is from register 0 to, or copy it to another register, and then tie it back to an address of a label. And so that would be included in your function. So all of these things are sub units of work inside your function definition. Okay. So it has to interpret the function. And so when we do an in or a cin in our case for C++, right? Then it's going to generate the signal for the keyboard, or out, it would generate the signal for the monitor using its, the registers and the data from those components. All right, so for instruction processing, using the von Neumann model, we would then looking at how the program and the data are stored as sequences of bits in the memory. So we wanted to really focus on how, right, data and instructions are stored in memory and read from memory. So the program is executed one instruction at a time under the direction of the CU, right? It is very sequential in that. that the control unit is going to read the instruction, interpret the instruction, and get ready for the next instruction. So what are some of the instructions in assembly? Right, these are just unit of work, and there are three basic kinds. Computational instructions like add and not. We can add, bring in value. We can clear, right? You saw this last time. We can do a not, and usually that is for the two's complement, or we can find, right, the reverse or the opposite for the bits. We can also move data. This could be load, store, load indirect, load effective address, store to register, load to register. And you do these register to register, so we clarified that later. We can also do control, and this, if you learn if else statement, right, loops, this is control instructions. You jump and you branch. And in Microsoft MASM and NASM, for those, you spell out jump, J-U-M-P. And branch is, spelled a little different. So syntax is a little different. So control instructions are using for conditional statement or control statement. Okay, so for 9, we're going to talk about the steps for instruction processing. So the first step is to fetch instruction from memory. Then it's going to decode the instruction. Step 3 is it's going to evaluate the address, where that is. Right, so it gets the instruction from the memory. It's going to decode it. It's going to say, oh, where is that in the memory? And for step 4, it's going to fetch the operands from the memory. And operands could be add and load. So let's say that it gets an add. It's going to execute that. Add what, right? So it's going to find the value from the registers or the registers with the fill, right, to a label. And so with that, it's going to execute the operation. But remember that we want to execute and store, right? Ultimately, it has to have some kind of numerical value. So we want to store the result. This is why you have the destination register. Like R0, R1, that's the first register on your line of code. So if I do an add, so for example, if I do like add R0, 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 R1, right? So your result is going to go here. And then the operands are here. Okay, so you have, like, let's say I have a 1 here and a 2 here. So it's going to be a 3. 3 is going to store in the destination register. And you can use different register, but remember R0's job is for in and out. So if you want something to be in, you have to use R0, something to be out, you're going to have to use R0. You're going to see that we're going to use R7 for jump a lot. So there's specific register that it's designed for specific functionality. Okay, so we talked about this. And then this is where I got that from. So you can refer to this image for that question. And it notes here that not all phases are needed by every instruction phase. It may take variable number of the machine cycles, so it could be varied. So when it processes your instruction, there are two parts. One is going to be your opcode. Two is going to be your operands. What instruction to do and what is it doing? Who is it doing it to? Operands. So I'm going to highlight the operands so you can see. Earlier we have add R0, R0. I'm going to use R1 and R2 so that way you can see. So these are all registered. Let's say that we have values or something initialized there, right? We already talked about operation. So the operands are these guys right here. Okay. Or we can do a load. R0. And then we can say label. Can't type 2, for example. And then down the line in your data section, you would fill what label 2 is, right? That's just an identifier to a location where we would store a data or a value or an address or something. Now for the opcode, what are the opcode, right? So we can use the same example, R0, R1, R2, and your opcode is this. Question. Okay. So for number 10, we already talked about the two essential parts, opcode and operands. What are their roles? Operations to be performed for the opcode. Operands, data, locations to be used. So I heard from student that digital logic is also covered in some physics class. I know people in the prior classes mentioned Dr. B covers some digital logic, right? I know that they cover that here in some physics class. I know if you do take other classes at university, they spend a little bit of time with digital logic as well. Or if you're in the electronics area, it's, they cover that with PLC. Okay. Any questions regarding opcode and operands? So when we say opcode, right, it's this. When we say operands, it could be values or it could be register. Okay, so in the next part, it talks about instructions are encoded as a sequence of bits, just like data, but not always. And it has fixed length, 16 bits or 32 bits or, certain size. So the CU interpret the instructions, it would then generate control signal to carry out the operation. So remember that we are using, right, integrated circuits. So for our embedded system, what we would see is that it would generally generate an electrical signal for the operations, right? And we're going to see this in the lecture for the upcoming weeks, where we'll see what add is in binary. Okay, so your simulator is really good at giving you the bin and the hex file. And then when you look at that, you would see the 0 and the 1s. So when you do an add, look at the 0 and the 1s. The first 4 bits in that word is going to be your opcode. And that indicate whether it's add or load or LEA or, store, ST. Okay. And from that, we would have the execution, sometime completely, sometime not at all. Okay. So I talked about opcode being 4 bits. It's going to start from bit 12, which is, or bit 15 most left. And it's going to go 4 to the right. So that's going to be 15 to 12. Remember how we read, right, representations of bits before in our prior session? So from the most left, 4 to the right. So that's going to be the opcode. We talked about register 0 through 7 for the 8 general registers. This is used for temporary storage. And so in this example, I have register 0 as the destination register. Here's my opcode. Add. What am I adding? My operands are whatever value in the register 0 and another 0, a hex 0. This is x0, so hex 0. So at this point, my destination register 0 is 0. Okay, assuming that I don't have anything in here. Let's say that this is my first line of code. Then my register 0, the destination register store this. Okay. So when we add, right, we would see the first 4 bits. It's going to look like this. So at the signal level, the 0 and 1s, you're going to see 0, 0, 0, 1. And in this case, it's using the value here for the register 110. This is used to indicate which register. This is for destination, where it stores the result, the next 3 bits. So the first 4 bits is for the opcode. The next 3 bits, right? So this is going to be the destination register and then your operand. Your source register is here, bit 6 through 8. It's going to skip this. This is used for flagging. And then for the last 3 bits, from the least significant bit, bit 0 to bit 2, that's going to be the other source register. Okay. So in this one, it says add content from register 2 to the content of register 6 and store the result in register 6. So we would say add. Here is the destination. That's the result, register 6 for this one. And then it's going to add the content from register 6 to register 2 and put it on register 6. Question. All right, so for the load, we normally load label, okay, or values. Most of the time you load label, which is a location where you can fill values. And this is for reading data from memory. We're going to go to that location to read the data where we fill. This is used for flags. You will see later where this turns 0 and 1s, what that indicates. Okay. Yeah, that's just a signal that's used for specific things, and we'll talk a little bit about later. So right now, I want to focus on these 3, understanding that, and then you will see how this ties in. For the loading part, we can load to the location, and we're going to read from that location and put it to register 0. So this is called the base offset mode. And what that does is it's going to add the offset to the base register in the result. The result is going to be the memory address. So we tie this to an address. And what that will do is it's going to load from the memory address into the destination register. So label 1 is just an identifier for the location, right, where we store the value. So it's going to take that address of label 1 and put it into the register where it can read the data. You can do an LDR. Okay, this is for the offset. So this is load direct. That's going to be load directly. And so for the LDR, it's going to load from the register. And you notice here that we can do an LDR, R2, R6, R3. We don't use the label here, we use the register. And that register can be tied to an address already, right? Load is really for memory. So in the prior line, we will likely have to have the register 3 loaded to an address. Then we would do an LDR. I normally don't like using LDR because that's an extra line of code that I have to load to another register to load to another register. So in order to use LDR, you have to preload the other registers, these operands, to be loaded to the third register. Okay. So I rather just load from the label and fill the label with the value. So direct load it just saves time. But you know, if you have the reason to use LDR, you can. So you're gonna see a lot of my example program for the lab. We're mostly gonna use LEA, LDI, and LD. Okay, because otherwise we have 2, 3 extra lines to load and it just becomes more complicated. So just reduce the work. All right, for fetch, this is the load the next instruction from the memory into the IR. So it's going to take the address from the PC and put it into the IR. This is when it fetch. Then it's going to copy the content, which is the address from the PC, to MIR. Then after that, it's going to send a read signal. Then it's going to copy the content from the IR to, or the MDR to the IR, the data to the IR. After that, it's going to increment the program counter so that way it can go to the next instruction. So once it fetched, it needs to get ready for the next instruction. So in the fetch, it loads your instruction, right? Take the address, put it into the IR, copy the content of the program counter to the MAR, read, then get the data into the IR, and then get ready for the next instruction. And that's in the fetch. In decode, this is for the first 4 bits of the instruction. So that will be your opcode. And it's going to be corresponding to whatever that you're trying to do, add, load, store, etc. Like LDR or add. Okay, so for if the instruction is fetched, we can put down those steps from the notes. It's going to load the next instruction at the address of the PC into the IR, load the content of the PC into the MAR, send read signal, read the content from the MDR, and store in IR. It's going to increase the program counter because the program counter just really track where it is in your code. So for the next instruction, so that's going to point to your next instruction, which means that it needs to do a +1. This is really important because we manually have to do this in the future for stacks. right? So the PC plus 1. Think of it like an array, right? We have to increase to the next one for the next instruction. Any question? Okay, so now you can find that from page 6 and 7. So here's some fetch operands. Obtain source operands needed to perform operations. We can load data, we can read the data from the register using add. So we can do an LDR or we can do an add. And so to bring data in, you can have, let's say, I can give you some example. So let's say I can do an add. Let's say I want to do register 3, R3, and let's say I wanted to do a number 5. That means I'm adding decimal 5 to register 3 and place it on register 3. Or it could be another register, right? But let's say register 3 has nothing. I added 5 to it and then put it back to it. Okay. Then I can do a load LDR. Let's say we're going to put that onto register 6, right? We would do register 3. Let's say we're going to load 2 operands. Let's say that comes from register 2. And let's assume that register 2 have something or 0. So it's going to take this value, and then put it on here. Now we can do it without the LDR. If we do the LD directly, right? What we can do is we can load it to the label, or we can say that we would load it register 3, right? We can say label 1, and then on label 1 at the bottom, we would do a dot fill. We would do, let's say, a hex 5. Okay. So that means that I fill the value to label 1 as 5. So I initialize that here, and then it's going to point to that location that has hex 5 and load it directly to register 3. Okay. Now on this one, normally you have to clear. So I will tell you that, let's say that I wanted to clear register 2 to make it 0. So I have to do something with that. So this is going to mean that register 2 is equal to 0, right? And then register 3 is equal to 5, or hex decimal 5. And then now we would load that. So we actually load the 5 and the 0 to the register 6. So this doesn't mean that it's added. It just load the address of decimal 5 and that's hex 0 to register 6. So if we want to do an add here, we would do an add there. So that will be equal to 5. Okay. This is loading the address of the location where it stores 5 and 6 to register 6. Any question?
So they're both loading a value to that register?
No, it's loading the location of the values to this register.
Okay.
Yeah, where if you do an add, I'm going to give you the example of the add, right? We can do the same thing. Let's say that we use these two lines, right? Register 3 has a 5, register 2 has a 0. If we do an add, register 6 now with register 3 and register 2, at this point, register 6 is equal to decimal 5 plus 0, which is 5. Where this, our comment should be load address of is it decimal 5 and hex 0.
Okay, so R6 is pointing to both R3 and R2?
Yes, that's correct. When you do a load, it points to read the R2 and R3. But when you do an add, right, you read the data from the actual register. Or if you do a load direct would load. But normally we load the location of the value. It's just a way to go read the data from a location. A question? Good questions. Okay, so execute. This is for operations, how it's using the source operands, right? So when this happens, a good example is it sends the operands to the arithmetic unit. It would, in our case, like here, it would add the signal. It would use the add signal to add. Okay. But when it load and store, it doesn't really need to execute. It just store, because store is write and read is just, it's going to go to the location to read the data. Okay. So when you know, in our case, we only use add. In other assembly language, it uses like neg or negate to subtract, but ultimately the processor add the two's complement. So to simplify, the author or the creator of LC3, they decided that add is like the easiest one. So you just need to remember one instruction. You can add the negative value, or you can add the two's complement, which is equivalent to subtraction. Okay, so that's a lot simpler than other assembly language. For store result, we write to the destination in the register or in memory. And earlier we talked about writing. So we always put the result in the destination register of the add from the operands. And the result of the memory would then be placed on the destination register. Or we can use it for storing instruction where the data is stored into memory. So in the write situation of the store, it write the address into the MAR and the data into the MDR. We talked about that earlier. And then it activate the write signal. So for 12, it says, when should control instructions be used? And control instructions, we talked about jump, where we can go from one location to another. So in a loop, right? So for example, in a for loop, what you do is you jump, right? I would have, let's say, loop 1 is the label. And I can have it loop, so it's gonna do the arithmetic, and then I'm gonna subtract or increment 1. Because remember, in the for loop, in like a C++, you have when it starts, right? When it ends and how it updates. And normally we would do an increment. So if I want to go from 0 to 5, right, I need to go from 0 and then +1 and then +2 and then +3 until it gets to 5, and it's going to exit the loop. It's going to stop. right? It's going to stop the loop and it's going to continue in the program. So in that case, what we will do is we will branch to a positive. We'll talk about branching later. So as it's going to, as long as it's checked for the condition, if it's true, we can do that with the while. So it's going to increment, or we can have it decrement. It's going to subtract until it gets to 0. So when it gets to 0, it checked for true, then it's going to stop the loop. So a control instruction is really used to change your sequence of instructions. Instead of going to the next line and the next line, we can have it come back to the loop 1 and then continue to do that until it's not anymore, and then go to the next line. Or we can do a jump from one section of your program to another section of your program. Okay. And branching is very either the same or, close in other assembly, right? Sometimes they spell out jump, like I said before. Sometimes they spell out branch instead of BR. And in this case, we're going to talk about the flag. So earlier, somebody asked me, what's the bit 5 for, right? It's for this. When it's 0, positive, or negative. Okay. So we're going to look at that later. Okay, so in the next part, talked about changing sequence of instruction. We just touched on that. For loop, if, it's just if then, but in C++ and other languages, if else. In Python, if elif, right? Elif. Or in the case of function call, when you do recursive function or function call, so let's say I have a function calling another function instead of recursive, right? Like I said, function 1 calling function 2. So I'm simply using a label func1 and then do something there. And then from there, I'm going to jump to func2 or have it continue to func2. But what if my function 2 is down the line in my code, right? I have other things going on here, so I can have it jump to func2 or jump back to the function 1 if I don't want to do recursive, a function calling itself. And it also does return RET in LC-3, so you can return from a function and then, come back to the beginning of the function again. So you can use that for function call as well. Okay, so when you have special need instructions or changing the content of the PC counter, so in the control instructions, it's gonna update the PC based on how you want your program to move or how the instructions needs to be used. Okay, instead of just do a +1 for the next line or the next instruction, it's going to update it based on whether you have a jump or a branch. Okay, and that signal for that bit is very important. It's going to go, when it's going to check true or false. So 0 is for false, 1 is for true. And so in the case that it checked true, right, it either exits the loop where it continues in the program, which is a +1 in the PC, or if it's false, right, it might come back to the beginning. So it's going to update the PC to come back to the beginning of that loop, go back to the loop 1 label. We'll spend a little bit more time on control statement and loops in a few weeks. Okay, but this is giving you overview. So some of you are kind of getting it. It's if you can really visualize how your program should flow, right? Some of you just like naturally come up when you design your program, you're like, oh, I wanted to do this and this and this. And so if you look at how your program should flow, you can really think about like how you can control your instructions. It's a lot easier for assembly to really kind of see it. Okay. So here's a jump. We go to a base, so it's going to refer to the address for that label. So I can jump to like label 2. And at label 2, I just simply do an add or something there. Okay. So in this case, it's going to come back here. And then in this section, it's going to do this. It's going to execute these things. So this is really what's happening of all the things that we talk about, right, in the control state. Okay, it's the PC goes to the memory address register. It's going to increment for the next line. Then it's going to get the address to get the data. Then once it got the data, it's going to put it into the IR, take the content of the IR and decode it. That's for your opcode right here. And then it's going to execute your opcode. And then it's going to check again whether it needs to. So if it needs to jump back, it's going to come back here and it's going to redo these things. Okay. So that's how it's really, when you write if else statement or loops or, function call, it's like that. And so once the instructions is no longer needed to process for the application, right? Then it's going to process the instruction from the OS side. So the OS is, we talked about how it manages processor and other resources. So, if you're in computer science, you're going to have a class where, they're going to touch on, or you probably took a class that talks about OS design. And so in that case, what you see is that it's really looking at how processes can be queued, right? Like Aiken asked earlier for NQ and DQ. So in other resources on how the OS is really managing the IOs and be able to control the processes within. So when we build application that's running on top of the OS, a lot of the things are already been handled by the OS. Okay. But in some cases for us, when we code it, a lot of the times we can manage it within the application. And then in other cases, we would require the OS to be able to incorporate some system resources for our application. I do this a little bit in my advanced Python class. Where we touch on like how we can tie in some of the using the library that just use the OS resources to incorporate in our application. Okay, so let's answer the last one and then we'll call it a night. And then I'll share some resources for Gate. Okay, sorry, running low on time. How can the computer be stopped from processing? What you can use is you can use the AND operator for the clock generator to generate with 0. And that would mean that the CU is going to stop seeing the clock signal, so it stops processing. It uses the clock to be able to continue. Okay. So we AND the clock generator with 0. Remember that when you AND anything with 0, right, it becomes 0 because right, we talked about like true or false. So if you have 1 is true and with 0, you're going to get a false. So when you AND anything with 0, you're going to get a 0. And so when you get a 0, the clock stops. And if the clock stops signal, then it stopped processing. Like this. So coming back to last week when we talked about gates, right? This is the AND gate. And here's your clock generator. You AND it, and then you would have it with the 0, then it's going to stop running. So it needs some form of signal, which is here. So if your signal, your voltage dropped to 0, then it stops. Any question? Okay, so a lot of the information also came from your notes, your chapter, and also if you look at the PowerPoint from the publisher, you can also pull some stuff from there. But please read. I think it's important to kind of get the sense of how the content, I did summarize a lot of it, but you know, when you read the chapter, a lot of the times coming back to it's going to be a little bit clearer for you. Okay. I will stick around for questions. Please put your name in the chat or your attendance. I'm going to go ahead and stop recording.